everyone. My name is Luis. I'm a postdoctoral researcher in the Institute of Physics and Mathematics in Morelia, Michoacán. And this is my present work, which is called Thermal Diffusivity of Oil in Water Emulsions Stabilized by Sodium Dodecyl Sulfate and Ionic Surfactant, or SDS surfactant. And well, emulsions are colloidal systems which consist in drops of some liquid suspended in another liquid phase. In this example are drops of oil in water, and emulsions are usually stabilized with surfactants which are placed in the interface between, for example, oil and water. And usually emulsions are characterized by transmitted light or light scattering, but we are interested in the thermal characterization of this kind of systems. And for this purpose, we use this experimental setup, which consists in a lacking amplifier that sends a sinusoidal signal with amplitude and the frequency under control, and it is sent to a laser driver so that we can obtain a laser beam with amplitude and controlled frequency. So that laser beam is sent to a silicon wafer, which acts as a wave generator, as a thermal wave generator. It converts the light from the laser to thermal differences, and that differences in temperature are measuring with a piezoelectric sensor, and the signal from the sensor is sent to a impedance coupler and then to a preamplifier, and it is sent again to the lacking amplifier. So in this instrumental amplifier, we can make an operation between these two signals to obtain a new signal without noise, and it's a signal with an amplitude and a phase. Well, and we use this equation, the heat equation, and we look for the thermal diffusivity, which is this parameter alpha. Yes, and the thermal diffusivity gives us information about how efficiently and how fast the heat can flow through a material. Yes, so in this equation, in the right side, we have the differences in time, the derivative in time of the temperature, and in the left side, we have the heat flow Q and the derivatives in space and time of the temperature. And yes, if we solve this differential equation in one dimension and under some considerations, we can find this sample solution, which relates the voltage obtained in the lacking amplifier, the amplitude and phase, which a function which contains the thermal parameters. In this mu is contained the thermal diffusivity alpha. So we can separate this equation in the real part and the imaginary part. From the imaginary part, we obtain a linear equation directly, so we can plot the phase and the versus the sample thickness, and the slope of this equation have the information of the thermal diffusivity. And from the real part, we can linearize the equation taking the logarithm of both sides, and if we plot the logarithm of the amplitude versus the sample thickness, we obtain this linear behavior, and again the slope of this line have the information of the thermal diffusivity. So we can obtain the diffusivity from either of these both plots. And this is our first results. Before starting to measure emulsions, we start measuring surfactant solutions only with surfactant and water. So this is a thermal diffusivity of our system with SES surfactant. And in the inset, we have the thermal diffusivity for small concentrations. For small concentrations, the surfactant is suspended as in the form of monomers, but just in a special concentration, the surfactant starts to form micelles, in this case, spherical micelles. And this point is called the CMC, the critical micelle concentration. And we observe a discontinuity just in the CMC. We don't consider that this is exactly a minimum. Maybe it's just a discontinuity. And the other points are the diffusivity for higher concentrations. And we can obtain also the thermal conductivity. As we know the thermal diffusivity, we can obtain the thermal conductivity if we know the heat capacity and the density of our materials. So as we know only the effective thermal diffusivity of the whole system, I mean the surfactant molecules with water, we can obtain effective thermal conductivity using the law of mixtures. And in this plot, we have the normalized thermal conductivity versus the volume fraction of the surfactant and the touched. Here I am plotting two surfactants, two experiments, well, a set of experiments. The black dots are surfactant, are micelles of CTAP, a cationic surfactant, and the blue squares is experiment with SES micelles, which is an ionic surfactant. Yes, and the dashed line is the fit with the Lewis-Nielsen model, which is an effective thermal model which takes into account the shape and orientation of the particles. In this case, the particles are our micelles. And the information of the shape of the particles is in this A parameter. And this parameter phi m is the maximum volume fraction that can be reached with some geometry of the particles, some particular geometry. We see a good agreement with the model in this plot, with the theoretical prediction, with our data, but there is a phase transition reported previously in the literature for these surfactants from spherical micelles to right-lock micelles. So we consider that fixed parameter A is not so correct for the description, is not a complete description, and we proposed a parameter but as a function of the volume fraction. So we proposed a polynomial function, and this is the new plot taking the shape parameter A as a function of the volume fraction. And we see, again, a very good agreement with the theoretical prediction. And if we plot the function A, our new function A of the shape of the particles, we observe a minimum. It is not shown here, but the minimum matches well with the point where the phase transition occurs. And finally, this is the kind of emulsions that we are fabricating now for the second step of the experiments, which are made with microfluidics. And well, as a conclusion, well, we are starting now with the emulsions. These are our first results. As a conclusions, we regard that the thermal wave resonant cavity technique that we used is useful for the characterization and for the observation of phase transition of these kinds of systems. And we regard that this technique is also able to determine the thermal conductivity of the material itself, in this case, the surfactant molecules, or more complex systems as emulsions with surfactants. And as future research, well, we are conducting similar experiments, but with emulsions. In this case, oil in water emulsions, but we hope that we can observe maybe the transitions between oil in water to water in oil emulsions, the inversion of emulsion. And finally, this is my contact information. This is the link to my institution and my email. If you have more questions or if you want to collaborate, we are happy to discuss. And thank you for your attention.